want to welcome you to the second session of our Spring Aquatic Academy. And again, I want to thank Dr. Dominic and Margaret D. Cristofaro, who supported this course and made it possible. Tonight, we're going to look at the ocean from space. Remember that the title of this course is Making the Case for Ocean Exploration. And these guys with NASA, they get all the money. He's going to try to convince you, though, that sometimes looking back at the ocean from space tells us things that we could never learn otherwise. And he's right. Josh Willis grew up in Texas. He got his bachelor's degree at the University of Houston. And then he headed west and he got his PhD in oceanography at the Scripps Institution of Oceanography, where he studied ocean warming and sea level rise using the predecessor to the Jason missions, which were the Topex Poseidon. And we created the first public exhibit about Topex in Boston a long time ago. These missions were called one of the most successful oceanographic experiments of all time, and they revolutionized the field of oceanography. And I think they do serve as a reminder that spaceborne instruments are the only way that we can get a synoptic picture of large parts of the ocean at any given time. And it's a combination of research from space and research from ships and buoys and submersibles and all of that that puts it all together. I learned something quite interesting about our speaker. He not only has a PhD in oceanography from Scripps, he has a master's in comedy from Second City in Los Angeles. And they produced a comedy about climate change called The Lollygaggers. It's about a 45-minute play, and we've made a deal that we're going to try to have it performed here at the Aquarium sometime in the next few months. And it's a sketch show about a group of characters who are experiencing climate change. It's a musical, or there's music in it anyway, comedy. And he went to the Second City to take this program because of his belief that we have to be much more effective in communicating with the public about these issues like climate change, and is convinced that comedy is the way to do it. So please welcome Josh Willis.
Oh, do you guys hear me okay? Everybody? Great. Thank you, Jerry. That was a lovely introduction. You're much too kind. I'm really not that funny, but hopefully you'll laugh a couple times along the way here. Oh, I need my pointer. Hang on one second. Well, thank you very much, and thank you so much for the invitation and the lovely dinner. I'm very full, but I had coffee, so I shouldn't fall asleep while I'm standing. But if I do, somebody just nudge me. So what I want to talk to you about this evening is really looking at the oceans, as Jerry said, and in the big picture, because one of the most I think important things that we do at NASA is look back at the Earth. You know, we think about NASA, we think about the Mars rovers and the Hubble Space Telescope and the astronaut program, the space station, and all these things are things that NASA does. But really, and this has been part of its charter since the beginning, NASA is supposed to be looking back to understand and protect the home planet, our planet Earth. And so it's had a long history of measuring the oceans and other things from space. And so what I want to talk to you about tonight is how we do that, and a little bit about why it's important. And I always start off talks like this with this picture. It's one of my favorite pictures of the Earth. And it's fun now. It's quite common now because you can go out and get Google Earth and you can play around with the Earth and spin it around and look at it in any direction you want to. And if you were to just rotate this view just a little bit this way, the only thing you could see on Earth would be the Pacific Ocean. The Pacific Ocean covers almost a third of the entire planet. And of course, we all know 2/3 of our planet is covered with water. So when we think about things like climate change and global warming, and just the business as usual of our planet Earth, we're really talking a lot about the oceans. Arthur C. Clarke once famously remarked that we really misnamed our planet. It shouldn't be Earth, it should be ocean, because that's what most of it is. So to get a view of this thing, it's so big, you really have to back way out in order to see the whole thing. It's a simple idea, trying not to see the old saying about the forest for the trees. That's definitely true in the ocean. We really need to get far away in order to see the whole thing kind of all at once, just like you do in this picture. So why is this important? And I want to jump right into this discussion a little bit about climate change. Because again, and I'll talk more to this in a second, but we think of climate change and global warming as something that's happening in the atmosphere. This is the record of the average temperature of our planet's surface over the last 130 or 40 years. And it's increased by about 1.5 degrees Fahrenheit, something like that. And it's projected to increase several more degrees Fahrenheit over the next 100 years, depending on how much fossil fuel, how much fossil fuels we burn. But again, this is something that's happening to the atmosphere, right? This is how we think of global warming. But in fact, if you think about it for just a second, the way global warming works is we get this energy from the sun, which strikes the Earth. It's a huge amount of energy, way more than we could ever possibly use. Most of it is absorbed by the surface of the planet. It goes right through the atmosphere. It comes in the form of visible light, and the atmosphere is transparent to this visible light, so it just goes right through. So some of it bounces off clouds and other things, but by and large, most of the energy that the sun sends us gets absorbed at the surface. Then the surface warms, and it radiates energy back out towards space. So the surface of the planet is trying to send this energy back out. But the surface of the Earth is much cooler than the surface of the sun. So rather than sending out the energy in the form of visible light, it sends the energy out in the form of infrared radiation, this sort of long wavelength radiation. And it's familiar to you. You guys have all probably seen infrared cameras where you can see the heat pattern and so forth. And it's this kind of energy which is trying to escape off the surface of the planet and make it back out into space. But the difference is that the atmosphere is not transparent to this kind of radiation. And some of it gets absorbed. In fact, it gets absorbed and re-emitted and absorbed and re-emitted as it goes and tries to make its way back out through the atmosphere. And the amount that's absorbed depends on what's in the atmosphere. So as we add carbon dioxide to our atmosphere, we're actually trapping more of the heat that would otherwise make it back out to space. So the question is, where does this heat go? And because I'm an oceanographer, you guys already know the answer, right? It winds up going in the oceans. In fact, over 90% of the heat that gets trapped this way is going towards warming the oceans. So even though I showed you that picture at the front about the increase in temperature of the atmosphere, really all the action is in the oceans. Over 90%, 93.4 according to this calculation. So that warming atmosphere, all that energy that's required to heat up the atmosphere by that degree, it's a big planet, it's a lot of surface area, that's all here in this 2.3%. It's a tiny fraction of this heat. So, like I said before, it's planet ocean, and it's ocean warming, which is really the issue when it comes to climate change. Now, yes, question?
So the ground, continents, only takes up 2%?
Yes, that's right. It's because although the heat capacity of the rocks is non-trivial, they do hold a significant amount of heat. It just doesn't heat that deeply. You know, if you drill a hole, it's dense, and it doesn't go far. It doesn't go that deep into the ground. In fact, But the ocean can carry that heat 4 kilometers over its entire depth. So really the ocean is this incredible heat sink on our planet, and if it wasn't for the oceans, we would have already warmed up a whole lot more. In fact, it would take only something like 10 years for global warming to happen for a given amount of CO2 if there was no ocean. But because there's an ocean, it actually takes something like 1,000 years because the ocean's slowly mixing that heat down into its deeper layers. Sometimes I do a demonstration. I didn't bring with me tonight, I'm sorry. I should have. But if you take a balloon and you fill it with air and you hold a lighter to it, the balloon will pop, right? But if you fill a balloon with water and you hold a lighter to it, it actually won't pop unless you use a blowtorch. Then it will pop. Or one of those little light, the little ones that shoot. Yeah, those will pop. But a regular flame actually won't pop a balloon filled with water, and the reason is this heat capacity of the water. The water is just so good at sucking the energy out of the balloon that it doesn't heat up, it doesn't melt the rubber. So yes, but make sure if you do that at home, you get adult supervision. So what about this heat going into the ocean? Well, one of the things that the oceans do in response to taking up this extra heat is expand. Literally, the water in the ocean, as it heats up, gets bigger and it takes up more room. And this is one of the drivers of sea level rise. Of course, the oceans are also rising because the glaciers and ice sheets are melting, but about 1/3 of the signal is literally just this warming. And what's interesting is if you look back over time, this is some actually recent work that I'm really kind of excited about. It shows a 2,000-year record of sea level. And it's fascinating the way they do it. They actually look in these salt marshes along the east coast where the land has been sinking for millennia. And as it sinks, there's a very small tidal range. And there's little critters that like to live in very certain ranges of the tides. And so they drill down these cores and they can go back and reconstruct past sea level with an accuracy of about 10 centimeters in the vertical and about a decade along the time axis. So it's really exciting, and if you look, you see this period where basically sea level was not rising at all. It was totally flat for 1,000 years. And then it rose a little bit at a rate of about 0.5 millimeter per year in this period which is called the medieval warm period. So this is a period of warming, particularly in the northern hemisphere. We think this might have actually had something to do with the ocean. There's people speculating that it might be related to this thing called the overturning circulation, which is a big, slow-moving, sometimes referred to as the conveyor belt, or the Great Ocean Conveyor Belt. But anyway, if you follow the record, then there was a little ice age starting about 500 or 800 years later, and it cooled a little bit. There's some hint of cooling, although not much fall and not much drop in terms of the sea level. And then right here at the end of the record, you have this 2 millimeters per year, which is equivalent to the global number over that period. And essentially, this is one of the ways we know that it's really the Industrial Revolution that's been driving this warming and this rapid increase and the rapid sea level rise. But there's nothing like this anywhere else in the last 2,000 years. So we know this last 100 years is markedly different. And this is, anyway, this is one of my favorite new little pieces of science that's come out in the last few years. And there's actually several records like this now, all up and down the US East Coast. But I'm here to talk about NASA, and one of the things that we do that I think is the most important at NASA is we have satellites we build in collaboration with the French called the Jason missions. And Jerry actually mentioned this at the very beginning. The very first mission was Topex Poseidon. This is the mission that got me my PhD, I'm happy to say. And these are missions that literally measure the height of the ocean from space with an accuracy of about 1 inch from 800 miles up. It's an amazing technological feat. It's really incredible that they work, and also that they are so accurate that if you average all of the observations together over a 10-year period, they cover the entire Earth, and you can get an accuracy for global sea level, which is in the range of a few millimeters. This is what allows us to see things like sea level rise. And my furry friends here, are experiencing the effects of sea level rise. This is a great movie, by the way, Ice Age 2. I really enjoyed it. Sea level rise is the bad guy. It's funny. But anyway, they all live. Not to spoil the movie for you. They all live. Everyone makes it. But our sea level satellites have been going since the early 90s. And you can see this incredible precision that they have. And what's fascinating to me about this record is that they're so accurate, you can see the seasonal cycle of global sea level going up and down. Now, you would think that this is because of the warming and cooling of the oceans, because of the sun. But in fact, that largely cancels out between the northern and southern hemispheres. And a lot of this signal, this seasonal up and down, is actually tied to the transfer of water back and forth from the land to the continents. So the atmosphere is so good at sucking up water and carrying it around that it actually lowers the level of the oceans by about 1 centimeter in the northern hemisphere winter. And this water rains down over the land. Remember, most of the northern hemisphere is land and most of the southern hemisphere is ocean. So there's a big discrepancy between north and south. And this water lands on the land and it runs off over the course of the year. And you can see this yearly up and down of the oceans, essentially breathing. The planet sort of, you think of it like the planet breathing. So it's an amazing tool. You can measure the water cycle. And interestingly, here in 2010 and 11, there was this massive El Nino, and I'll talk a little bit more about this in a little while. There was not a massive El Nino, but it was a moderate El Nino followed by a huge La Nina. And it shifted the rain patterns around so much that a huge amount, a centimeter or more, of global sea level was lost to rainfall falling over the Australian continent. Then after the course of a year or so, most of it ran off and our sea levels continued to rise. But we can talk about all the little bumps and wiggles in this, but of course the most striking feature of this image, this plot, is the 6 centimeter rise in global sea levels over this 20-year period. So that's a rate of about 3 millimeters per year. So the historical rate was less than 1 if you go back thousands of years, millimeter per year. The rate over the last 100 years was about 2 millimeters per year, and the rate over the last 20 years is about 3 millimeters per year. So there's a hint, it's just right at the detection level, but there's a hint that actually the rate of sea level rise is accelerating as well. And this is something that we really couldn't measure without these missions. You can go back a couple. Without these missions. The incredible precision of the Topex Poseidon mission and its follow-on, Jason 1, Jason 2, and soon to be launched this summer, Jason 3, are such that we can actually measure this with a precision that was completely unthinkable before. So again, this is one of the most important and kind of like biggest picture things we can measure from space. If you think about sea level rise, of course the causes for these, the physical causes for these are twofold. I mentioned this earlier. You've got the melting of glaciers and ice sheets. This water is running off and eventually collecting in the oceans, causing sea levels to rise. And you've got the thermal expansion from the direct warming of the oceans. So these two things added together are essentially what you see in this curve. So in a sense, this is one of the most powerful indicators we have of how the planet's climate is changing. Welcome. How you guys doing? Great, good. I meant to say this too also at the beginning. I'll just use this short break to get it in here. If you have questions, feel free to stop me at any time. I love answering questions almost as much as I love the sound of my own voice. So please just throw up your hand at any time and feel free to ask me anything you want. And if I don't know, I'll make it up. Yes, please.
Okay, on the slide just before, the top right-hand corner, it seems that the spread of temperatures is wider, and at the bottom left, it is more dense. Now, what accounts for that?
Well, there are some small.
Repeat the question.
Oh yes, right. Yes, thank you, Jerry. The question was that these measurements seem to have a bigger scatter around this solid blue line in the later years than they do in the early years. You have a very sharp eye. So essentially, the color changes between these three different times are changes in actual missions. So the red was the first Topex Poseidon mission, green was Jason 1, and orange is Jason 2. And these missions, we're really pushing the capabilities of these missions to make this kind of observation. Remember, the accuracy is about 1 inch for a single measurement, but when you average over the entire globe, you can get an accuracy of just a few millimeters. But everything has to be going really well. And so some of these bumps and wiggles have to do with small errors and uncertainties that crept into the very first mission, Topex Poseidon, and have kind of been propagated through. And so as you get to later years, some of the things that we were kind of correcting out of the first mission don't get quite corrected out. In particular, one of them is the tides. So the tides are a very large signal in the oceans. They can be many feet as you fly around. And because we only cover the oceans once every 10 days in a complete pattern, we don't resolve the tides at all with the satellites. However, they fly in a very particular orbit which allows you to, over time, sample the different phases of the tides and eventually understand them, model them, and remove them. So some of this scatter has to do with the fact that when we removed the tides, we used the data from the very first satellite. And it had some slight peculiarities to it, and we removed not just the tides, but some other signals having to do with how the satellite works. It's pretty technical. I can tell you more if you want, but the short answer is that essentially there's small errors and they're peculiar to each satellite. So this most recent satellite has a slightly different set of errors, and actually more recently updated versions of this plot, they're getting better. They're starting to understand all those tiny little signals that are left when we average all the data together and remove them. So someday we hope to see that the scatter is almost gone in this line. And we continue as a scientific community to look at these smaller and smaller signals and errors and try to understand them and either model them or average them out and so forth. But yes. Well, I've never gotten that question on this talk before. You're eagle eyes over here. So just to give you a little bit of an idea for how these satellites work, it's one of the simplest measurements you can make of the ocean from space. Essentially, there's a radar on board the satellite, and it shoots a radar wave at the Earth, and it travels down, reflects off the surface of the ocean, travels back up through the atmosphere, and by measuring the length of time it takes to go down and come back up, it tells you the distance between the satellite and the surface of the ocean. Now, if we know the position of the satellite very accurately, then we can state the height of the ocean, and we can watch it change over time as the satellite revisits these places once every 10 days. So there's a whole bunch of positioning systems on the satellite as well. There's a GPS system, just like the one you have in your car, but maybe a little fancier. There's another system called DORIS, which is sort of like GPS, but from the Earth. Instead of having the satellites in GPS, they send signals down toward the Earth, and DORIS has beacons on the Earth that send signals up. Then the last thing is there's a little mirror, and they bounce a laser off of it every once in a while and measure exactly where it is. So all these three things together tell us very accurately the position of the satellite with an accuracy of about a centimeter in vertical height. Then the timing tells you the distance, and so you do a simple subtraction, and that's how you calculate the height of the ocean. But there's a lot of things in the height of the ocean. It's kind of interesting because the ocean height changes for all sorts of reasons. One of the main reasons the ocean height changes is because of currents. It turns out that when there's a big current in the ocean, the forces that it feels as the Earth is rotating cause the surface of the ocean to tilt. So literally, this satellite was invented in order to measure that tilt of the oceans and tell us about the ocean currents. But in addition, the height of the ocean can also change just because of the pull of gravity. So if you have something like a mountain or an island, literally the pull of gravity from that mountain will cause the water to pile up around it. So another thing that you see is sort of the influence of the shape of the seafloor. So if you have a trench, then there's less gravity, the water actually falls away. So one of the main things we measure when this flies around is what's going on the bottom of the ocean. And I'll show a little bit more of that later. And early on, the great challenge for this type of measurement was to separate those two signals from each other. Yes?
How wide a swath does it take?
It's about a 5 to 10 kilometer footprint, and it looks straight down. There are new satellites in the works. Go back again. There's one called SWAT, which is going to launch in 2020, which will actually measure a swath. It'll sweep out a swath of about 100 kilometers on either side, and have an accuracy about, or resolution about 1 kilometer within that swath. So it will really be revolutionary in terms of the improved resolution that you get. But that's a little ways off, 5 more years. Yeah, anyway, I'll talk a little bit more about this later, but yeah, keep in mind, it's a very simple measurement, and so in a lot of ways, it's one of the most powerful measurements that we have from space because it's so simple. We don't have to do all these wild corrections or a lot of guesswork about what it is we're really measuring, which some of the other missions do. Why is this important? So why do we need to measure the height of the ocean and the currents? Well, one of the things that we do with JSON data is look at currents in real time as they change. We really have a spectacular view of the oceans from space. When you get 2 or 3 or 4, in some cases, satellites together, you can really measure this tilt in the oceans, and you can see the currents very clearly. In April of 2010, of course, the Deepwater Horizon catastrophe occurred. There was an explosion aboard this rig, which was drilling in the Gulf of Mexico, and many lives were lost. It was a major disaster, but eventually the platform itself sank and was lost. But the oil continued to bubble up, as you know, out of the bottom, out of the hole that they were drilling through. And it formed a major slick on the oceans. There's been a whole oceanographic campaign to study it, and the movement of the oil is quite complicated. They recently discovered some of it actually sank, interestingly enough. But a large part of it made it to the surface, and data from these missions, the JSON missions, was used in real time to track the surface currents and predict where the oil slick would travel. So it's an incredibly powerful tool for the for real-time oceanography as well. It's not just climate science.
All those different colors. Radar paths, radar stripes?
Yeah, these are the different missions. The paths here are the different, the ground tracks of the different missions, right? JSON 1, JSON 2, and IndySat. Then the background colors are actually the difference in height. So this is a tall, warm patch of water. And to the left of it, it's cooler and lower. And because it's tilted this way, we know that the currents are going perpendicular to that tilt. Yes, question?
Is that a common thing? If it's taller, it's hotter?
Absolutely it is, yes, yes. Just like with ocean warming, global warming, tall water tends to stand, or warm water stands higher. So a lot of what we see when we look in the data from these missions is where the warm water is. So, and it's not just the surface water. Actually, I have another slide in a second where it's the warmth of the water over depth that really matters. So you get a big stack of warm water. It will literally stand many centimeters or sometimes a few feet higher than colder water. So another thing that we want to measure now is over time, we're actually able to build this 20-year-long record of sea level change with these satellites, because all the satellites, Topex Poseidon, Jason 1, Jason 2, and hopefully Jason 3, have overlapped. So we've actually been able to tie together the records from the different missions into one long 20-plus year record of how the oceans are changing. And it's really fascinating. If you look at the 20-year trend in sea level rise, it's not flat. You might expect from global warming that we're adding water to the ocean, it's warming, expanding, it would kind of rise everywhere the same. But in fact, it's quite complicated. In the Western Pacific, it's warming 2 or 3 times, it's rising 2 or 3 times as fast as the global average number. And over here in the Eastern Pacific, along our coast, it's actually falling just slightly. In the last 20 years, we've had 0 to a slight drop in sea level off of our coast here in California. And the reason is because of large natural cycles, just like El Nino and La Nina. These move heat around on the equator, and they change the sea levels. So there's another cycle called the Pacific Decadal Oscillation, which changes back and forth once every 20 or 30 years. Has a big impact on our fisheries off the coast, as many of you are probably already aware. A lot of what you see in this picture is the Pacific Decadal Oscillation, swinging from a very positive phase to a very negative phase. And a lot of this trend is the result of that. But some interesting work that was done very recently suggests that if you account for that natural cycle, there's actually still some sea level rise left that's not totally uniform. And so in fact, it's been suggested that some of this warming might be longer term than the natural cycles, might actually be related to changes in the winds, the natural wind pattern that's resulting from human-caused climate change. So it's one of the very first attempts to try and separate those two things out. This is a model that's kind of predicting what we would expect, and this is what's actually observed in terms of that human-caused component. So I mentioned this just a second ago. Another reason we are really interested in looking at the height of the oceans is because it tells us where that warm water is. And things like hurricanes really care a lot about where the warm water is, because that's their fuel. Essentially, they take heat out of the ocean. It causes convection and uplift, and that's the fuel that drives, the energy that drives the power of the storm. And this was a very interesting example. This is actually Hurricane Katrina. And it took this little looping path across the Gulf of Mexico. And if you just looked at the surface temperatures of the water, there's no obvious reason why it's sped up right here. But if you look at the ocean height, you see that it was actually traveling over this big warm blob, which is called a warm core eddy. There's a big current that comes through here, the Gulf Stream, and then exits out through around the southern tip of Florida, and every once in a while it breaks off a big warm donut. They're called Gulf Stream warm core rings. And actually the reason Katrina sped up just before it hit land is because it went directly across one of these. So the water there was warm not just at the surface but over depth, and as the hurricane goes along it churns up that water. And if it's just a thin warm layer, then it doesn't necessarily gain extra fuel. But if it's a deep warm layer, then in fact it can cause the hurricane to spin up. Now this doesn't happen to every hurricane. It's got to be a particular set of conditions for this to happen. But clearly the data would have been incomplete if we didn't know about the sea surface height. So yes?
Was that data available at the time of the hurricane, or did this happen after the fact?
It was, and right around the time of Hurricane Katrina was when hurricane modelers began using this type of data in their hurricane predictions. So there's, of course, a lot of what drives the path of the hurricane is the atmosphere. It's almost entirely atmospherically driven. But the strength of the hurricane does depend on the warmth of the water that it's over. And so the use of this data right around this time, which began right around this time, was one of the biggest improvements in prediction skill for the strength of hurricanes that they've had in many decades. So the data is being used, but it's fairly recently, really. We've had this data around for 20 years. It's really only the last decade or so that it's been used like this.
What's AOML?
AOML is a NOAA lab in Florida. I forget, Atmosphere, Ocean, Marine Laboratory, something like that. If I was making it up, that's right. AOML. And that's National Oceanic and Atmospheric Association. Not the guy who built the boat. So I mentioned earlier that we also use this data to literally probe the seafloor. And this is one of the most fascinating uses of the data, I think, because whenever, as I said before, whenever you have an underwater mountain, the force of gravity literally causes the water to pile up around it. So if we know the height very well, very accurately, we can map the seafloor. And this is a map that was generated based on sea level data. It's got other data over the land, but over the ocean, this comes from our altimeter, these missions that measure the height of the ocean from space. And interestingly, one of our recent satellites, Jason 1, it died 2 years ago now, I think, in 13, but just before it did, we moved it into a slightly different orbit. And instead of repeating once every 10 days, it had a very long period orbit of about 400 days. And what this did was it made the ground tracks spaced very, very close together. And this improved the accuracy of these kinds of seafloor maps quite a great deal, quite a lot more than they had been in a long time. And it's a little difficult to see, but in fact, this map, which includes that data from Jason off its normal track, shows a few seamounts and a slightly sharper image than this one. If you look at the details here, you can really start to see little underwater mountains and so forth. Yes, you can tell it. And that the mountains are actually a little sharper and more clearly defined. We have a lot of information already, so it's not super obvious. But if you look in great detail, this was a major sort of scientific development because essentially, if you kind of look at how big seamounts are and how many of them we can count, then as you get to smaller and smaller ones, we expect more and more underwater mountain. We expect to have more and more there. And essentially, there's something like 100,000 seamounts that are predicted to be there, but we don't know where they are. And so this kind of data is kind of helping to close the gap. Now, I mentioned earlier that we have to separate this out from the kind of ocean signals, right? If you have a current that's tilting the sea level, it would look different. And one of the ways we do that is because the seamounts don't move, but the currents do. So we subtract out the time average, but and we get that we get a good average by having a long data record over the same tracks. And also there's some other processing tricks and things like that too. But literally, these satellites are exploring the ocean depths from 800 miles up in space. I talk about global warming a lot, which means that according to federal mandate, I have to have a picture of a polar bear. This is my polar bear picture. This is from 2007, and he's way out there. In 2007, of course, there was a minimum in the Arctic sea ice. And Arctic sea ice is important for polar bears because they use it as a hunting grounds. They eat seals, which are better swimmers than they are, but if they sit up on the ice and perch and wait for them to go by, they gain sort of a tactical advantage. Well, in this summer, there were actually reports of polar bears swimming as far as 60 miles in search of sea ice, and many of them not being able to find any. Now, I'm not a biologist, so I don't really know what I'm talking about, but polar bears will probably survive somehow they can always just move south and eat Canadians instead of seals. But nevertheless, this reminds us that these large-scale impacts are beginning to be felt by kind of top-level predators. And I use that to introduce this topic of another thing we measure from space, which is ocean relevant, is sea ice. And this is usually measured by radars and other things which work slightly differently than our altimeter, but same principle. You bounce a radar wave off, and based on the return, you can either tell that there's ice there or not. Now, every year in the summer, the Arctic begins to melt. It gets warmer, and the sea ice retreats. And so this was from 1979. It was the sea ice extent in 1979, measured by the first satellites to look for the sea ice. And this is the sea ice in 2008. And you can see that it's retreated by about almost half the area, is gone. And I didn't just cherry pick these two. If you look at a record of the sea ice extent over time, there's clearly a long-term trend, and here's 2007, which was that record year with the picture of the polar bear. So the sea ice is changing, and it's another reminder of ways that we measure really important things about our ocean from space. Without something like this, you could never recreate this with this kind of information with ships, because you really need to get this distant perspective in order to see something as big as the extent of the sea ice. I always put this slide in here because it's a little fun, and it was one of really the first in a long chain of these incredibly dramatic collapse of an ice shelf in Antarctica. So just to the left off the picture here is a piece of the Antarctic Peninsula. It's that little thing that sticks up into the Southern Ocean off of Antarctica and kind of points at South America. And on its eastern coastline, there was a major ice shelf. It was called the Larsen B ice shelf. And an ice shelf forms when glaciers actually flow off of the continent and into the ocean, and they form kind of a giant pillow of ice. It flows out, and ice is technically a liquid at this scale. So remember, the glaciers and things are actually flowing. They're like rivers of ice. And here they flow off the mountain, and they form this big shelf, and it's floating. And in 2002, a satellite flew over and took a picture of it, and you can see all these little dark spots. These are actually pools where water has begun to collect in a pool, and because the water is less reflective than the ice, it actually absorbs more sunlight and creates a deeper and deeper pool. It turned out there was warming going on underneath the ice shelf as well, and a few months later, the satellite flew back over and took the same picture, and that's the one you see on the right. And essentially, the entire shelf, which was something like the size of Rhode Island, has collapsed, and all this furry stuff in here are icebergs, which are the remnants of it. So it completely just broke into pieces. What's interesting was that oceanographers went back to this shelf, and they drilled sediment cores where the shelf used to be, and they found out that the shelf had been there for 10,000 years, at least, probably much longer, but it dated back to the last ice age. And it wasn't until the warming of the last century that it finally collapsed, which means it's the only thing older than Hugh Hefner to break up in the last 100 years. Told you I have a master's in comedy. But I need a little rim shot. I need a little. Thank you. Thank you. That's your job from now on. Another one of my favorite satellites to talk about in sort of NASA's suite of Earth observing satellites is called GRACE. And GRACE is really an amazing technological feat too. It's a pair of satellites, and they chase each other. They're actually called Tom and Jerry. And they chase each other around, and whenever one goes over something heavy, the pull of gravity literally causes it to speed up. And by measuring the distance between them very accurately, you can infer the weight of whatever you're flying over. So literally, this pair of satellites weighs the continents. We have a sketch about this, Jerry, in our show, The Lollygaggers, which hopefully you'll all get to see. And if they weigh something like the continent of Greenland, they find that Greenland is actually losing mass. It's been on Jenny Craig and lost about 2 trillion tons in the last decade. And it's interesting, you can see not just the long-term decrease, but you can see the seasonal cycle. So every year, in the wintertime it snows and the mass goes up. In the summertime it melts. And of course the glaciers are always flowing ice off into the oceans as well. But this up and down is clear in the data, but also you can see the overall loss over time. And it's interesting to look at the patterns. I'll talk just a little bit more about this at the end. But there's a pattern where you have ice loss in the southeast quadrant, but also in the northwest as well. And it turns out that this is partly because the oceans are warming the glaciers from the edges. So it's really kind of a fascinating story, which we'll come back to. Another measurement we make from space is the color of the ocean. Literally, these are just visible pictures. It measures the visible light which comes back out of the ocean. And if a certain amount of the light makes it past the ocean surface, and you're actually seeing reflections of the little critters, the phytoplankton and things. And they can use this to get a sense of chlorophyll in the ocean. And if you look at the long-term record of chlorophyll, it looks something like this. So this is data from CWIS, and now there's a whole bunch of these satellites. I'm just trying to get the picture of all of them in there. There's a whole array of these different satellites which measure ocean color. And this is kind of a composite picture of everything averaged together, but you can see in the subtropics, all major ocean basins in the subtropics have chlorophyll minima. And this turns out to be because these are regions where there's downwelling. The wind is forcing waters together and it sinks. They're also interestingly co-located with where you have the great garbage patches that you've heard about. Same process, the water's sinking and converging, and so the trash piles up there. But because the water's downwelling, it's not super favorable for phytoplankton to grow. The nutrients, they need light and nutrients, and so the nutrients are kind of being pushed down. So anyway, these are called, sometimes referred to as the ocean deserts because there's so little marine life there. Another thing we measure is salinity. It turns out that if you're looking down from space, the brightness of the water depends on 2 things. One is the temperature of the water, but the other is the salinity. So salty water is slightly less bright. And if you know the temperature because you've measured it separately, you can actually separate those 2 things. And we've been measuring salinity from space for the last 3 or 4 years now with a mission called Aquarius. And there's other missions that are also adding on to this data set. Another thing we measure from space is rainfall. If you look at the tops of clouds, the cloud temperature tells you a little bit about rainfall, but this particular satellite also had a radar which looks specifically for rain. It would literally bounce off the raindrops. This is a climatology developed by this satellite, and also again there's a whole bunch of these different satellites. In fact, they can look at not just where the rain is, but they can look at some level of the 3D structure of the rain. This was a major storm, although I forget which one, measured by TRIM. So we have all these different satellites that tell us different things. They tell us about the salinity of the ocean. They tell us about rainfall. There's other satellites that measure wind. We talked about the sea level. Really what we want to do as scientists is kind of put all these things together and try to understand them at once. And this is a little bit of a study that we published a couple of years ago where sea level actually dropped. And I mentioned this right at the beginning when we were looking at that record of sea level rise. And here the red curve is all of those observations together from all the different sea level satellites. But the seasonal cycle has been taken out, so you can see the background a little more clearly. And what you see is that in 2011, we had this massive fall in sea level. And it turned out that it was at a time when we had a large El Nino the year before, and a really large La Nina immediately after. And this movement of warm water around on the equator of the Pacific wound up changing the rainfall patterns in Australia as well as South America, and caused extra water to pile up on these continents to a degree that it actually lowered sea level. And Australia is kind of special because some of the basins there actually are closed. There's large areas where there's rivers that kind of all run inland instead of out to the sea. And enough water piled up in Australia that year to actually account for 1 centimeter, almost 1 centimeter of drop in sea level over the course of that year. Now, of course, eventually it evaporated back out, made it into other parts of the hydrologic cycle, and found its way back to the ocean. So at the end, you see sea level rising back up to this long-term trend of about 3 millimeters per year. But for a while there, we had kind of a wild ride in sea level. So this is exactly the kind of study that's really made possible by data from NASA satellites. And it's a good illustration, I think, of the need to get a large, distant perspective on the oceans. So it's really only possible to do these kinds of global studies with data from satellites like Jason and Grace and TRIM as well. We also looked at the rainfall and TRIM over rainfall over Australia using a different NASA satellite. So one last thing I want to talk about, because I've spent all this time talking about satellites, is a new project that I'm really excited about called Oceans Melting Greenland, or OMG for short. Got that one past the censors, I was amazed. I mentioned this just very briefly earlier, but if you look at the patterns of ice loss in Greenland, it turns out that the places where the ice loss is the greatest are also the places where the ocean is warming up the fastest. And it turns out that the glaciers in Greenland run right off the land and into the water. So literally, the edges of these glaciers are feeling the warmth of the oceans. And as the oceans warm up, those glaciers retreat. And as they retreat, they tend to speed up, and they can dump more and more ice more and more quickly. So we came up with this project to try and measure both the oceans and the ice together at the same time over a period of a few years, and do this using aircraft. And we were lucky enough to get picked out of a whole laundry list of other different proposals. We were selected last November, and if all goes well, we'll start this mission sometime this summer, if not 2016. But just to give you an idea, this is sort of a diagram of one of these glaciers, and you can see that the warm water in the Greenland area actually sits below the cold water. Now, usually in the oceans, warm water is on top because it's lighter. But here, it turns out that the warm water is very salty. It's very salty water from the Atlantic. And the cold water tends to be very fresh and from the Arctic. So we have this layer of cold, fresh water sitting on top of warm, salty water. And it's this warm, salty water which can climb up onto the continental shelf and then find its way into these underwater canyons which feed the fjords and the glaciers. And if it reaches, then it can eat away at the edge of the glaciers. So our aircraft campaign is designed to fly around and drop these little in situ probes. So these are actually one-time use CTDs, conductivity, temperature, and depth observations. And they fall by parachute in a little package out of the airplane. And when they hit the water, there's a float, and the float stays at the surface. And then it drops a small probe which falls through the ocean, measuring temperature and salinity as it goes. And then the float part, which stays at the surface, radios that data back to the plane. Then after about 15 minutes, when the observations are done, the whole thing sinks itself. These little probes we're going to fly around with an airplane and drop a whole bunch of them all around Greenland. And then also once per year, we're going to fly a radar over the ice and measure the ice height and look for thinning and retreat of the ice. So we're going to do these two things together over the course of about 5 years. And we're going to look for this relationship between where we have warming water and where we have rapid ice loss. Of course, there's also, I mentioned earlier that the warm water is kind of crawling up in these trenches. So we really have to know the shape of the seafloor well, and there's also a large campaign to do shipborne and airborne measurements of the shape of the seafloor in order to better understand how that water is getting up there and interacting with the glaciers. So I'm really excited about OMG, as I'm sure you all are too. And I just want to give you a quick overview of it. And I think with that, I will leave you with this parting thought that really sometimes in order to explore, we have to take a step back. And it's NASA's job to help provide that perspective that you get from space or from something like a big aircraft survey. So with that, I think I'll stop and answer questions.
We're going to start with a video that some of you in this room will probably remember.
These are extraordinary times, and we face an extraordinary challenge. Our strength as well as our convictions have imposed upon this nation the role of leader in freedom's cause. Now going on around the world between freedom and tyranny, the dramatic achievements in space which occurred in recent weeks should have made clear to us all, as did the Sputnik in 1957, the impact of this adventure on the minds of men everywhere who are attempting to make a determination of which road they should take. Since early in my term, our efforts in space have been under review. With the advice of the Vice President, who is Chairman of the National Space Council, we have examined where we are strong and where we are not, where we may succeed and where we may not. Now it is time to take longer strides, time for a great new American enterprise, time for this nation to take a clearly leading role in space achievement, which in many ways may hold the key to our future on Earth. I believe we possess all the resources and talents necessary, but the facts of the matter are that we have never made the national decisions or marshaled the national resources required for such leadership. We have never specified long-range goals on an urgent time schedule or managed our resources and our time so as to ensure their fulfillment. I therefore ask the Congress, above and beyond the increases I have earlier requested for space activities, to provide the funds which are needed to meet the following national goals. First, I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to the Earth. No single space project in this period will be more impressive to mankind or more important.
That was May 25th, 1961. This is January 2015. The ocean was never mentioned. Not one single word about the importance of the ocean, research, exploration, nothing. Why? So that's what we want to explore a little bit about that this evening. You've already seen this picture from Josh. wonderful picture of the Earth from space, and the world ocean covers 71% of it. It's the largest single component of Earth's living infrastructure, which is Earth's life support system for all life on Earth, including our own. This was an article, it's a very important article in Science magazine, one of the 2 international science journals, January 16, 2015, Marine Defaunation, Animal Loss in the Global Ocean. Now this demonstrates that scientists can't speak a language that most people can understand. But the New York Times, the Washington Post, and most of the other media picked it up. Ocean life faces mass extinction, broad study says. At least that conveys the message. And the point is that everything in the ocean is changing. The ocean itself, life in the ocean, human expectations for and of the ocean, and our relationships with the ocean. All of those are changing. And in the Science article, some of the ocean issues that they identified were that ocean's getting warmer. You heard that from our first speaker. It's getting more acidic. Overfishing, bycatch, bottom trawling that destroys habitat on the bottom, and habitat destruction also from other areas like aquaculture in mangroves, which they point out in that article, and the increasing encroachment by humans into the ocean. And all of these together are leading to mass extinction. Now the article points out that so far the ocean has been spared most of this. The extinction rate for the last 100 years or so is 100 to 1,000 times the long-term average. In the ocean, it hasn't been that, but the argument they make is that if we don't change the ways we're dealing with the ocean, that within a few decades we could have massive extinctions within the ocean or massive defaunation. So in the near future, we're going to look to the ocean for more energy, both renewable and non-renewable, more food, more medicines, more minerals, more transportation, more recreation, and more water, more fresh water. We're already doing that in south of here in Carlsbad. The largest ocean desal plant in the Western Hemisphere will open later this year. And there are other plants that are being proposed up and down the coast of California. And we do need more fresh water. So less than 10% of the world ocean has been explored. We're losing the life system that we depend upon for our survival without even knowing what we're losing. The loss of species due to extinction, as I mentioned, it's 100 to 1,000 times background rates, and some people argue, like Ed Wilson, that it's 10,000 times more than background rates. It isn't just that you're losing species. When you lose species, you lose biodiversity, and you lose ecosystem services, and those ecosystem services are things that we all depend upon for our survival. The ocean and the atmosphere are a coupled system. You heard that from Josh. This is a beautiful picture showing the ocean and the atmosphere, the colors. Throughout geologic time, they've done a dance. Sometimes the atmosphere leads, sometimes the ocean leads, and but most of the time throughout geologic time, this dance has been at a rate that animals and plants could adapt, or they could evolve rapidly enough to not go extinct. Sometimes it got faster, and perhaps the rate of change has never been as great as in the past couple hundred years. Some would argue that it even goes back to the beginning of agriculture 10,000 years ago. So change is coming, changes are already here, and the point is it's the rate of change that matters most. The rate of change, the second derivative. And this now, many plants and many animals can no longer keep up with the rate of change. So one of the things that if we really believe in conservation is we have to slow the rate of change. And the goal of conservation is not to preserve nature. Nature has evolved since the very beginning. The goal of conservation should be to slow the rate of change of nature to as close as it would have been in the absence of human beings. That would be an appropriate goal. Homo sapiens, well, let's see, sorry. So we are the most successful species in the history of life on Earth. There is absolutely no question of that. The question is, have we been too successful as a species? That shows what the population looks like, and I'm just showing how rapidly it has changed. Human beings appeared back over here 200,000 years ago is when the first Homo sapiens appeared. It took until the year 1800 or a little after to get to the first billion people. We got the second billion in 130 years, and we have been adding a billion every 15 years since that time, and we continue to add that many. For more than 98%, 99% of our history, we were hunter-gatherers. We moved around the landscape in bands of 10 to 20 people, extended families, and the Earth's carrying capacity at that time was estimated to be somewhere between 200 and 400 million people. We're at 7.3 billion, now on our way to 10 billion. Things really changed when we invented agriculture 10,000 years ago, because people then could settle down, they could form villages, communities became larger cities, they became empires, and this allowed the carrying capacity to grow up. And through a series of green revolutions, the carrying capacity of Earth continued to grow. So Paul Ehrlich, when he wrote The Population Bomb and said that in the 1970s there would be massive starvation, of hundreds of millions of people would die of starvation, he was wrong, because he hadn't anticipated the series of green revolutions that increased the production of food per acre. But the problem is now, according to the United Nations, we will need 70% more food by 2050 to feed a growing population. Agriculture already uses 70% of all of the fresh water on the planet. We do the same in California. Our agriculture takes about 70% of the available fresh water. We use more than 50% of the ice-free land to grow our crops and to raise our livestock. And when you think if we're at 7.3 on our way to 10, there's not enough land and there's not enough water unless we have quite a different kind of green revolution going forward. And agriculture takes a toll on the ocean. These are some of the 400 dead zones around the world ocean. You can see that one of the biggest ones is in the Gulf of Mexico, but all up and down the East Coast, Northern Europe. They tend to occur where you have large populations and runoff from human activities, particularly fertilizers, from agriculture and human waste, stimulate the growth of plants. And then when the plants die, they decompose, they use up oxygen, and these become dead zones, and the number of these is increasing. So agriculture takes a toll, takes a huge toll on the Earth. And the other thing are the kinds and amounts of energy we use in the air-changing Earth living infrastructure for life support system. According to the International Energy Association, we will need 3 times as much energy by the year 2100 as we're using now in 2050. 3 times as much. And the question is, where will it come from? Because the fossil fuels that we use now are already taking a toll. You can see the increase in CO2 there from 1960 up until 2012, or whatever that 2013, maybe 2012, continues to increase. And the real start of this was probably beginning with the Industrial Revolution. And in 2011, fossil fuels accounted for 81% of all primary energy use. And most of the experts predict that by 2040, the projections are that fossil fuels will still account for 78%. So we're increasing the percentages that we get from solar and wind, but if you start with such a small percentage, that the growth is modest. Earth is warming. We've already heard that. 2014 was the warmest year on record. 14 of the past 15 years have been the warmest on record. And the only way you can deal with that, you have to stabilize and then reduce the concentrations of greenhouse gases in the atmosphere. Once in the atmosphere, CO2 stays there a long time. Sometimes as much as 1,000 years, but certainly in many centuries before it gets transferred to the ocean. And if you look at the rise of CO2, starting back 400,000 years ago, human beings came in here, so there were obvious fluctuations before humans, but look what CO2 has done in the last short period of time. CO2 has never been above this line for 650,000 years. Our choices of energy, when you think about it as we go forward, what should be the criteria that we use in selecting our energy sources? We should reduce greenhouse gas emissions. High energy density is very important. That's the amount of energy you generate per unit area. Renewable, but not just renewable and green. Not all renewable energies are very green. Windmills aren't very green for the most part. They take up a lot of space. Every single windmill needs an access road so a pickup can go down and service that windmill. And if leaving large unfragmented chunks of nature alone is a key to conserving biodiversity, then we've got to look at these energy sources very carefully. And we should have a diverse portfolio that would be tuned to different opportunities. Go to Iceland, they have great geothermal energy. Not very many places that have that. There are some other places that have great hydropower. And if we did these things, though, it would begin to address the warming and ocean acidifications. I think it's clear from the science article and what lots of other people have told us, we have come to a fork in the road. Remember Yogi Berra said, if you come to a fork in the road, take it. And the question is, which fork? I love when Robert Frost poem, when he said, two roads diverged in a wood, and I took the one less traveled by, and that has made all of the difference. Part of the problem that we have within our ocean, with our conservation community, with our NGO community is we are so used to traveling the well-worn road, and it took us to success. But most scientists that look at the future are convinced we have to take a different road if we're going to avoid the kinds of things that we must avoid. So, marine defaunation, ocean life faces mass extinction. You look at that article, overfishing, bycatch, destruction of habitat by bottom trawling. There are approaches that we could use, although I was disappointed in the article it didn't mention. 90% of all commercial fish stocks are fished at or above sustainable levels. Demand for seafood is growing more rapidly than population. 91% of the seafood eaten in the United States and here in California is imported. Most of it comes from Asia. More than half is farm grown. Is that good environmental stewardship to fly fish from China here? This shows in the light blue, this is the catch, the wild capture fisheries worldwide. And you can see that for the last 2 decades or 3 decades, we haven't, in spite of increased effort, we haven't succeeded in getting more fish out of the ocean because they are fished at or above sustainable levels. All of the growth has come in aquaculture. We've had too many boats chasing too many fish, destroying the bottom, and throwing back a lot of fish that was unintended. That's bycatch. And it's something like 1/3 of all of the fish caught is thrown overboard, dead or dying, because that wasn't the target fish. There is an answer. It's environmentally responsible open ocean aquaculture. We've done aquaculture poorly in many parts of the world. We continue to do agriculture poorly in many parts of the world and parts of the United States. Do we stop eating vegetables and fruits and meats? No. So we should embrace this because it would take the pressure off wild stocks, it could meet the demand, and it's darn sure more environmentally responsible. If you look at this map, these are the major importers, and the yellow, those are the major exporters. You can see that Asia, China is the major exporter. We're one of the major importers. I'm not going to use the figures at the bottom because I don't think you can read those numbers. But there was a very interesting study recently done by the United Nations, and they did an assessment of all the countries on the planet, asking the question, which country has the greatest potential for aquaculture, offshore, open ocean aquaculture? And the US won hands down. We have the largest exclusive economic zone of any nation on Earth. That's the light blue in this figure. Every place you see the light blue. And it's the zone from the shoreline out 200 nautical miles. It's the zone where each nation controls the activities within that. And then they asked the question, how large of an area of the open ocean would you need using the best knowledge, the best science, the best technology to raise an amount of seafood equivalent to all of the wild catch? And their conclusion was it would take an area the size of Switzerland, which is very close to the size of Vermont. Now just imagine for a minute, take Vermont. Anybody here from Vermont? I'm prepared to give up Vermont. No, we may take that. Move it around in our continental shelf area. Wouldn't that seem like a good thing to do? California is one of the best places because we don't get the kinds of hurricanes they get in the southeast. We have deep water close to shore, we have huge demand, and it's even the per capita demand is greater than much of the rest of the country because we have wonderful ethnic diversity and they like seafood. We could have a safe, secure, stable supply of healthful seafood, and we could also add jobs. We could protect what's left of our working waterfront, and some of us in this room, Kim over there, me, we're working very hard to get a project approved here about 25 miles north of San Diego in federal waters, just outside of state waters. They have the investors, $45 million of investment to do something. And the argument that I made in Sacramento last week was, California has this wonderful ocean ethic. We should set the bar high, set this very high standards, but let's try a well-controlled experiment, and if it succeeds, then you can extend the lease in time and maybe in space, and if it doesn't, you can throw the bums out and keep the deposit, the bonds that they have to post. I think it would succeed. So, about the size of Vermont. So when I look at all of this, and I go to all these meetings of some of our colleagues, is it time to reboot? You said maybe you take your head out of the sand, look at things differently. I think we have to, in our community, we have to reboot. We've been losing the game for decades. So we ought to pause and step back. Remember, Will Rogers had a wonderful saying, if you find yourself in a hole, stop digging. We keep digging and digging and digging, and we are losing. Look at that figure. I think we need to reboot. You see this guy staring at this crazy tree, but if you look carefully, there's a face in there. There's one eye, there's another eye, there's a mouth. I think we've lost sight of what we're looking at and what we're trying to accomplish in terms of our ocean. these are just a few of the dates we have to keep in mind. Our Earth is 4.5 billion years old. We've had oceans for at least 4 billion years. Life formed shortly after that. Evolution continues. We had the first ancestors, the first hominids, 2 to 3 million years ago. But we've been only around for 200,000 years, and we have done more to damage the environment than any other species. And you have to remember that most of our impacts originate from human activities on land. The only exception, I think, is overfishing. You can argue that oil extraction from the ocean, and that is, but it's to a smaller extent. So the two 800-pound gorillas we have to deal with are the ways we grow and harvest our food, including seafood, and the kinds of amounts that of energy we use. And many current practices are neither sustainable nor do they make sense scientifically. There's general agreement that on the conditions in the world ocean now, it's unhealthy, overlooked, and it's a mystery. We all want it to be healthy, valued, and understood. Where we get all the disagreement is how do you get from here to there? And while scientific opinion should prevail in getting from here to here, remember, Richard Feynman said, you don't improve the quality of a technical decision by asking a lot of uninformed people. Uninformed people, every one of us should have a say on the kind of a planet, kind of an ocean we want. But when I go to my doctor, I want an expert to tell me how to solve my problem. So we need to really work on that. We need exploration and research to better understand it, because we're losing it without understanding it. We need education to value it, and we need action in order to keep what we have. And I think they go in this sequence. So if this was a figure from the science article, and they said we're at the edge of a cliff facing massive extinction. And so this is the present here. There's a zero in there somewhere, right there. Okay, there's present. This is the past, and this is the future. So in addition to overfishing and habitat destruction, the creeping industrialization of the ocean was one of their major concerns. We know that we have to leave more space for nature, more forests, larger and more different kinds of ecosystems, and you do this by clustering human activities. I can remember when I was a graduate student, that was a long time ago, yes, we believed that 2 or 5 acre zoning was going to be what would save the environment. This was around Chesapeake Bay. And time has shown we were dead wrong. The best way to protect the environment is to cluster human activities, leave more land to nature. And I think in terms of the creeping industrialization, you have to look at what are the driving forces. And if you look on land, we zone our land. We keep bars away from schools. You do it through zoning. We allocate spaces to different functions. We've never done that in the ocean. We've never had the opportunity until July 2010, when President Obama signed the first ocean policy that this nation has ever had. It's for the oceans and Great Lakes, and in it, it was identified that marine spatial planning would be a key to conservation, and that you allocate spaces to nature, and we've done a great job in California of doing that through the Marine Life Protection Act. But you also allocate spaces to human uses that are compatible with a healthy environment and that would benefit the economy, and that we have not done. Marine spatial planning can bring order to an increasingly crowded ocean to protect values and uses. And one of the geographic information systems is a power tool for accomplishing that. And Jenny does a lot of that for us here. Those are the marine protected areas in California. And I say we've been a leader. No state in this nation comes close to what California has has done in identifying places that are of biological significance. How do we slow the rate of extinction? So we leave bigger chunks of nature, both terrestrial and oceanic, intact and unfragmented, and we slow the rate of change. This is what this aquarium is all about. It's the changing relationship with people in the earth and the ocean to make them more sustainable. It's really what makes this aquarium different from other aquariums. And we believe in it so passionately that we're going to add a wing at a cost of $53 million that is designed to tell this story. That's what it's going to look like. We're going to break ground in March of next year. This carries the architecture into the building, but the important thing is the path. When you enter, you first go into an art gallery. And the reason is that art often is a much better way to make emotional connections of people with nature or almost anything else than science. So this is where you make the emotional hooks. Then they go into a pre-show area where they're given a common vocabulary, a common set of facts. Then they go into an immersive 300-seat theater. Each seat is wired for interactivity. The screen is 130 feet long, 30 feet tall, and this is also a projection surface. When they emerge at the top of the theater. They go into a changing exhibit gallery that will feature live animals and some technology. And the hope is that people will look at those animals in ways they have never seen our animals before. And they will understand at a gut level that our future is tied very closely to the future of these animals. And we will be able to, we are starting to work on a game so people can take it with them and play a game to build a more sustainable world, looking at energy and agriculture. And they can get their friends and their families to join in on this game. And with all of the kinds of mass media and social media, we maybe can cast a long shadow. Let me just show you very briefly. That's just a view of the art gallery. This is the pre-show area, a lot of technology. And just before you go into the theater, it will pose the question, what kind of a future do we want to create? And it will draw upon Will and Ariel Durant, the historian's statement, the future never just happened. It always was created. We will create the future, either with purpose and intentionality, or we will create it by not being willing to reboot and think about what we're doing. That's a shot showing the screen, the disc in front, and it's big enough so that we can look at different alternative futures. And after you look at one on the whole screen, you could rotate it all the way over here, put another future in the middle, rotate it over there, another one there, and then that could dissolve to cover the entire screen. And it will be related to the decisions that we make. This is looking back at the seats from the screen. And as Tom Turning in the back has told me, if there aren't any more people in the seats when we open, Jerry, you're going to be toast. This is when you go into the changing exhibit gallery, and we think that this really is going to can be important. Somehow we have to get more people to re-examine the things that we've all grown up with in terms of conservation. Some of those ideas we don't like. And we live in a society where ideas are considered to be dangerous. And the best thing to do is to kill them as quickly as possible. And yet what we need to do is keep ideas in play like a game of badminton until we can really determine which of these ideas can help us. If you take an idea to Washington right now, it quickly goes either to the right or to the left, and then it's dead. Somehow, we've got to keep ideas in play and to understand the consequences of those choices for both humans and nature. And we believe it can be a grand future. But it's going to take a lot of fundamental change by a lot of people And it all depends on what we do. So our challenge is to design and create a new planet right here on Earth. And that's what we're hoping all of you in this room are going to help us do. Thank you.